All right. Hello, everybody. I'm here to talk about how we are helping build the open and interoperable geospatial platform for the Metaverse. My name is Shahzan Mohammed. I lead 3D engineering and ecosystems at Cesium. And I'll go through a quick introduction of what we do at Cesium and then tie that into 3D tiles, which is the open standard we work on, and then move on to game engines and specifically O3DE from there. So Cesium's history is born in aerospace. One of the first projects that Cesium was built for was to visualize satellites in space. And the reason I bring this up is because precision and accuracy all the way from space to the ground has always been at the heart of what we do. It's been a core requirement, and as we see going forward with the data capabilities that are being captured today, this is becoming more and more important. So one of the main things that we've seen over the past 3 to 5 years is how the collection and dissemination of real-world data has changed. What we are seeing is that data is being collected faster, more frequently, and at higher resolutions than ever before. And this is presenting an interesting challenge because the amount of data that's out there being disseminated into various types of devices and use cases is just exploding. And for us, the main goal is how can we create a single platform that can allow us to fuse all of this data into a single engine, a single scene. So regardless of how you're collecting the data, where you're getting it from, whether you are capturing the data yourself or you're purchasing it or getting it from open data sources, it shouldn't really matter. There should be a central place or central places that all work using open standards that can consume all of that data and help you build the applications that you need. So essentially, it's more about bringing the data to where the developers are at, rather than asking the developers to adopt their pipelines to custom engines and custom workflows for diverse types of data. So at Cesium, we are essentially building this platform at the intersection of computer graphics and geospatial. A large part of our team, especially the engineering team, has backgrounds in 3D graphics. We take a lot of inspiration from game engines. SIGGRAPH is a conference that we love as well. So taking all of those concepts and then applying them to geospatial applications to enable the global streaming of data and helping people build industry-specific applications and engines based on that. So open source, open standards, and open ecosystem has been at the very foundation of what we've built. Cesium started with CesiumJS, which is an open source custom-built engine on WebGL. And ever since day one, we've always had the community and open source at our heart. So to give you a high-level view of the Cesium platform itself, the engines are, for most part, open source. All the runtime code, the streaming algorithms, all of that is open source. But the engines themselves don't have data. The data is coming from a variety of different sources. And Cesium makes that easier by having a SaaS platform called Cesium Ion, where we have global curated content, terrain, imagery, buildings, photogrammetry, that can be then disseminated into all of these game engines using 3D tiles. The Cesium Ion SaaS platform also allows you to bring in your own data. So let's say we are in the Fairmont Hotel here in Austin. If somebody wanted to fly a drone and create a 3D model of Fairmont, you can then bring that into the engine of your choice as well by having it tiled and processed on Cesium Ion. And once that happens offline, then you can stream an unlimited number of times into these applications. So 3D tiles is really the conduit standard that is enabling this dissemination of data across different engines. All of these engines on the lower part have different properties to them. CesiumJS is based on WebGL. Unreal is a custom, is again one of the leading engines, and then O3D is where we are at today. They have different ways of building their worlds and their scenes, but with 3D tiles, we're able to say, you process your data once, and then you can bring it into different scenes all at the same time. So let's dig into that a little bit, and let me share what 3D tiles is and then where we are taking it forward as well. So 3D tiles itself is a standard for streaming massive heterogeneous 3D geospatial data sets. What that means is, regardless of what type of source data you have, you'll be able to convert it into 3D tiles and then stream it into these engines. It's built for both visualization and analysis, and that's a key part there, because you just don't want to visualize the data, especially when you're thinking about metaverse applications and stuff. Being able to analyze, being able to visually inspect and do things with that data become important. An example is you have the door handle, and if you're able to identify which vertices and textures represent the door handle and which way the door opens, then you can create an immersive interactive experience with that. So 3D tiles really has three main parts. It's the spatial index that defines the hierarchical level of detail. It's the 3D payload, that's gLTF, and the analysis that comes with that, and the metadata. So at the heart of 3D tiles, the 3D payload is all done as gLTF. We use gLTF 2.0 for that, and because gLTF is increasing in adoption, that means switching runtimes, let's say going from CesiumJS to Unreal to O3D, becomes that much more easier. And again, because we are all about open source and open standards, we have helped contribute significantly to the gLTF specification as well. So 3D tiles itself was standardized around 2018. We've been working on it from around 2016. So there's been a lot of evolution, not just in the standard and in the industry, but also in how we capture and process data. So for that, we're working on upgrading to 3D tiles 1.1. It's an upcoming revision of 3D tiles that we expect to be standardized pretty soon. And there's three main goals for it. It is, how do we take data that has been, data and the standards itself that have been more for visualization and basic analysis to take into account the modern AI algorithms that are coming up that can then help classify and create more metadata for our 3D models of our real world. So semantic metadata becomes a significant part of it. With essentially going from being able to add metadata per vertex to adding metadata per pixel is what we are aiming for. The second major update is implicit tiling. In the 3D tiles image I showed before, all the spatial indexing had to be done by you. You had to define what the spatial indexing was. With implicit tiling, what we're introducing is saying, here's my bounding region, here's my subdivision scheme, whether that's octree, quadtree, and then you don't have to define that explicitly. The runtimes are able to compute that for streaming the data. This allows for random access and more performant massive simulations and analytics. The third thing that we're doing is making it gLTF front and center. Before gLTF was embedded in wrapper formats, essentially, that we call batch 3D model and instance 3D model. Now gLTF is at the core, and the metadata is embedded into the gLTF itself. So let's take a look at a few examples of how this works. So this is, on the right is an image that's from the 3D tiles overview, as we call it. And essentially what we're doing is enabling the streaming and dissemination of real-world data with semantics that come from AI and machine learning. So increasing the granularity, I mentioned that we are going from per vertex to per pixel, so that is a big part of the push here. So a couple of examples visually. So what we are essentially going from is, instead of having it be, let's say, per building, you click on a building and you get its height and its location, now you can find which textures and which vertices represent where the windows are, where the doors are, how the door can open. And then you can also identify trees on the road. And if you're able to identify those kind of things, let's say trees on a road or lampposts, which are very rudimentary, you can then replace those inside the game engines, because game engines have rich 3D models of such geometry already built in. So now you can enhance the immersiveness of your scene as well. So all of this means that we have to write streaming engines that take in 3D tiles. So the core part of those engines are being able to understand the place on Earth that you're looking at, and then being able to select only the data that you need and stream that over the web. So I have images of New York City, Manhattan here, and what you're seeing is that from the position of the camera, you can figure out what is in your scene, and then based on your viewpoint, you will stream higher resolution data up front close to the camera, and then lower resolution in the background. So this allows you to always have limits on how much quality and how much rendering you're doing, so that you're never overwhelming the type of device that you're rendering on. So that brings us to the runtime engine side. And before I get into O3D itself, I want to introduce Cesium Native to you. So Cesium, as we started working on game engines, starting with Unreal and then with O3DE, the decision that we made was that we understood that the 3D tile streaming algorithm, the gITF processing, the geospatial math for converting lat-long into XYZ coordinate systems, all of those things were essentially agnostic of any game engine that we would want to integrate with. So we created a library called Cesium Native that had all of these components that are game engine agnostic: the 3D tile streaming, the glTF serialization and deserialization, and the high precision geospatial math. What we are able to then do with that is reuse that library and just add on the components that are game engine specific around it. We, of course, did that with Cesium for Unreal first, which we launched in 2021. And then O3D, which I spoke about last year, but really it launched as a 1.0 earlier this year. So if we take a look at the architecture, what we are seeing is that the Cesium Native part is completely reused, and we just add on components that are specific to Cesium for O3DE. So components like the Cesium Ion integration, which allows you to bring in assets from the cloud, or how the camera and the streaming algorithms interact with each other. So all of that goes in O3DE, and then you can add in Cesium Native that is really the foundation behind it. So we've published this as a gem, and though it's open source on our GitHub, so you can definitely try it out. So what this essentially allows us to do is, because we already had Cesium Native when we did Unreal, it really allowed us to, at a very high speed, advance and build our pipeline with O3DE. So something that took visualizing a city-scale photogrammetry tile set, which took about 8 months because we were building everything from the ground up. It took 8 months in Cesium for Unreal. It only took 3 months with O3DE. So that's the scale of reuse that we're talking about. And as we go and add it to more and more game engines, we're going to see that kind of speed just add on and benefit as we integrate with other engines. The other thing that this does is, as we add features to Cesium Native for any game engine, that means they essentially become free to add for all the other game engines as well. So this is a really nice benefit of having that foundational library. So I want to show you a video that we made when we announced Cesium for O3D being launched. And here you see all the geospatial scale, the photogrammetry coming in. So I'll just pause and let this play. So, so essentially, after seeing that video, what we've essentially done with these integrations with game engines is that we've brought in, or brought together, essentially, two very, very different industries that had their own advancements in their own parallel tracks. So the geospatial industry and the software for that had been advancing in its own train track, essentially, for the last 3, 4, 5 decades, with mapping and cartography. And then game engines were making their own advances through the 90s, the noughties, and the decade we've had before. But they've never actually intersected. We've never had a game engine that could fully and interactively and at real-time speeds render the entire world. And similarly, we've never had a 3D geospatial simulation system with all the physics, the water simulations, the characters, the agents that could process all of that. So by combining both of these through gems and these plugins, we are able to bring those two fields together, and now we are seeing really amazing applications being built with these technologies together. So let's talk a little bit and dive into how we've integrated 3D tiles into O3D itself. So the first part is let's get gLTF rendering using the streaming part. So we're not even talking about 3D tiles here. Let's get gLTF working. And the great thing is that O3D already has all the material support for gLTF. The standard PBR material properties are all supported, which had a tremendous benefit when we started working with it. The other thing that had a significant benefit was multi-threading. Because of the way the APIs are structured, the model assets and the material assets are all able to be processed in worker threads, so we are never essentially bottlenecking the main thread and slowing down that process. And then we use the mesh feature processor to create all the drop packets in the main thread. And by combining all the vertices into those packed, so they're all batched and packed into single buffers, we gain a lot of performance while processing those gLTF that are streaming at runtime. Again, as a reminder, all of this data is coming at runtime. This is not something that you burn into the application or the game that you're building. It's all coming in at runtime to the user. So it's important that we not have bottlenecks on this data as it's getting processed. So the way Cesium Native and O3D interact is first there's the gLTF resource manager that is taking in the gLTF and processing it. From there, what we do is from O3D, we get the current view state. We understand what the camera is looking at, what's the field of view, is it a top-down view, is it a horizon view? And based on that, Cesium Native is essentially able to calculate which tiles and which cities you're looking at, essentially. So if you're looking at New York, you don't have to stream the data for San Francisco. You only get the data that you need for your scene. From there, we run those selection algorithms and then get them from the cloud, process them, and then pass the native objects to O3D for visualization. So the other thing that we have to solve as part of adding 3D geospatial at high accuracy and precision is floating point precision. O3D is no different from the other game engines, and they're all built around 32-bit precision. And I have an example here of the numbers that we see and the differences that we see between 64-bit and 32-bit coordinates when we are talking about the entire globe. So converting latitude, longitude into an Earth-centered XYZ coordinate system, we can see anywhere from a few centimeters to over a meter of precision, depending on which part of the Earth we are looking at. So for the Cesium office, which is based in Philadelphia, we can see anywhere from 10 inches just in reducing 64-bit to 32-bit precision. And what that means is, even though your camera may be stable and you're looking at one part of the scene, in every draw call, your geometry is going to be moving around. And this is called the jittering effect, where it feels like you're in you're holding a jackhammer kind of thing, and it's completely bouncing around, and you're not able to get fixed geometry. So the way we solve this is by changing the coordinate system to not be Earth-centered, but really the origin of it is on the surface of the Earth, close to where the camera is looking at. And this is called east-north up. So here's an example of San Francisco, where it shows the coordinate system being close to where the camera's at. So all your vicinity, essentially, is localized, and that way you can maintain precision. What this also means is that we have to keep updating the origin as we are moving around the Earth. So if we were to, let's say, fly from San Francisco to New York in the same scene, in the same level, we have to update the origin, because if you have the origin in San Francisco and let's say you're looking at New York, you're going to have enough difference in precision that you'll start to seeing the jittering effect again. So we always move the geospatial reference in the engine. So some of the other possible solutions also include creating sublevels. This is a concept we use heavily in Unreal Engine, where within the same level you can divide the scene up into sublevels. So you can, for example, have a sublevel for each city, and then you can fly between those and define the origins for those sublevels itself. So the other thing that I wanted to talk about as part of doing this for the metaverse and connecting with different organizations through these open standards is the Metaverse Standards Forum. So when we talk about the metaverse, what we see is that there's not going to be one standard or just one set of standards that are going to define how we work in the metaverse. What we are really seeing is that there are going to be different standardized standards development organizations like Khronos, like W3C, IEEE, the Linux Foundation, Apache, who are going to be developing different standards. But it's important that all of these standards, they talk to each other and are interoperable between each other. So the Metaverse Standards Forum is essentially a place for all of these standard development organizations, along with companies and the industry, to help create and interoperate between these standards. So the vision for the Metaverse Standards Forum is to be a venue for cooperation between the SDOs, standard development organizations, and companies to foster that development of interoperability between standards for an open and inclusive metaverse. So what this is designed to do is essentially, while we are developing the standards, these open standards that we believe will help drive the metaverse forward, is to have pragmatic, actionable, and exercises, essentially, that help us define how the interoperability works as well. And this isn't a part where we are saying the Metaverse Standards Forum is essentially another place to define the standards. No, the Metaverse Standards Forum is not going to be defining any standards. What it's doing is it's getting different people and different organizations into the room to talk to each other and help define the requirements from the perspective of different industries and different use cases, so that there's more interoperability and enhancements in how we create these open standards. So Metaverse Standard Forum launched in June with 37 founding members. Cesium was one of them. And unbelievably, I don't think anybody imagined this, by October, we are at 1,800 members in the Standards Forum. And all of these organizations are going to be talking at as part of different working groups, helping solve different challenges. So essentially, all of these organizations are going to be dividing their work into different categorizations and industries. We're going to see consumer, financial transactions, tokenization, file formats, and interchange. All of these become working groups within the Metaverse Standards Forum, and different organizations can take part in it and help drive the interoperability forward. One of these examples is how the 3D formats are going to be able to talk to each other. We are seeing a lot of interest in USD as the authoring format within the Metaverse. gITF is a fantastic format for runtime streaming. And how can all of these essentially work together and help talk between these organizations so that we are helping define the way forward for how content creation might work in the Metaverse. So this is just one of the exercises. We are going to have a lot more of them. And if you're interested, I would definitely recommend taking part. So the asset interoperability testbed is essentially to confirm behaviors and attributes are satisfied. So I mentioned how different industries can bring their different requirements. So that's essentially what is going to be happening in this working group where those requirements come in, and we run experiments for how the standards should interoperate between each other. So the call to action here is essentially if you're interested in these standards, if you're interested in adding your voice to these discussions, that you get involved in the Metaverse Standards Forum, and let's all make these open standards highly interoperable with each other. So conclusion for my talk, Cesium for O3D, it's out there. We'd love to get your feedback on it. It's open source, and you can create a free Cesium Ion account to get your data from the cloud, and we'd love to see what you build with that. And with that, I'll take any questions if there are.